So, okay, good morning one and all. So in the last session we have discussed about H plane T, E plane T and magic T. Okay. So what is H plane T? What is E plane T and what is the magic T? So H plane T junction is formed by cutting a rectangular slot along the width of the main waveguide. Okay, H plane T junction is formed by cutting a rectangular slot along the width of the main waveguide. So and attaching another waveguide. So the side arms are called H arms. Okay. So H plane T consists of 3 ports. 1, 2 and 3 ports. In the E plane T, a rectangular slot is cut along the broader dimension of a waveguide and side arm is attached. Okay. So in the E plane T, the phase shift between port 1 and port 2 will be 180 degrees. In the magic T, the rectangular slots are cut both along the width and breadth of a waveguide and side arms are attached. Okay, and it has 4 ports, port 1, 2, 3 and 4. The magic T has 4 ports. Today we will discuss about directional coupler. Directional coupler, right? So what is a directional coupler? See here, in this we are having 4 ports, port 1, port 2, port 3 and port 4. Port 1 and port 2 are main waveguide and port 3 and port 4 are secondary waveguide or auxiliary waveguide. Secondary waveguide or auxiliary waveguide. So directional coupler is a 4-port waveguide junction. Directional coupler is a 4-port waveguide junction, right? So how many ports are there? 4 ports. So it is a 4-port waveguide junction. They can be designed to measure incident power, reflected power and SWR values. So here the directional coupler is used to measure incident power, reflected power and the SWR values. Okay. So to measure incident power, reflected power and SWR values, we are using the directional coupler. It consists of 2 waveguides. So directional coupler consists of 2 waveguides. One is main waveguide and second one is auxiliary waveguide. So it consists of 2 waveguides. One is main waveguide and the second one is auxiliary waveguide or secondary waveguide. So a portion of power traveling from port 1 to port 2. See here, a portion of power traveling from port 1 to port 2. Right? Here the power is traveling from port 1 to port 2. Is coupled to port 4, not to port 3. So in these 4 ports, a portion of power traveling from port 1 to port 2 is coupled to port 4, not to port 3. Okay. So this power is coupled to port 4. Similarly, the portion of power traveling from port 3 to port 4. The portion of power traveling from port 3 to port 4 is coupled to port 2, not port 1. Is coupled to port 2, not port 1. Okay. The portion of power traveling from port 2 to port 1 is coupled to port 3 but not port 4. See here, the directional coupler is used to measure the incident power, reflected power and SWR values. So it is a 4-port waveguide junction. So it consists of 2 waveguides. one is main waveguide and the second one is auxiliary waveguide or secondary waveguide. If the power traveling from port 1 to port 2 is coupled to port 4 and the power traveling from port 3 to port 4 is coupled to port 2. Similarly, the power traveling from port 2 to port 1 is coupled to port 3, not port 4. Okay? So the S matrix for the directional coupler is, see here, the S matrix for the directional coupler is, so it is a 4 port, it has 4 ports, so that's why the S matrix becomes S11, S12, S13, S14, S21, S22, S23, S24, S31, S32, S33, S34, S41, S42, S43 and S44. It is the S matrix for the directional coupler. It has 4 ports. Port 1, 2, 3 and 4. If the 4 ports are perfectly matched, to the junction, we can say that S11 equal to, S22 equal to, S33 equal to, S44 equal to 0. If the 4 ports are perfectly matched to the junction, S11 equal to 0, S22 equal to 0, S33 equal to 0 and S44 equal to 0. Okay, so we know the properties of S matrix. So from the symmetry property, we can write S12 equal to S21, S31 equal to S13, S23 equal to S32, S42 equal to S24, S43 equal to S34 and S41 equal to S14. So it is due to symmetry property. We can write like this, right? So there is no coupling between port 1 and port 3. There is no coupling between port 1 and 3 and ports 2 and 4. Clear? There is no coupling between port 1 and 3 see here. So there is no coupling between port 1 and 3. Similarly, no coupling between port 2 and 4. Okay. So there is no coupling between port 1 and 3 and 2 and 4. Then we can write S13 equal to S24 equal to 0. Okay. So there is no coupling between port 1 and 3, port 2 and 4. Then we can write S13 equal to S24 equal to 0. S13 equal to S24 equal to 0, right? Here port 1 is coupled to this one, port 4, right? Not to port 2, not to port 3. So we can write S13 equal to S24 equal to 0. And from the unity property, okay, so if you substitute this S13, S24 and all these parameters, then the S matrix will be like this. S equal to, so S11, S22, S33, S44 are 0. So here the 4 ports are perfectly matched to the junction, right? So in the place of S11 we can write 0. So next S12, so S13, here S13 equal to 0 because there is no coupling between port 1 and port 3. Next S14. In place of S21 we can write S12 from the symmetry property. Here S22 equal to 0. S23 and S24 equal to 0. Okay. Next, S31, here S31 equal to S13. Okay. See here, S31 equal to S13 and S13 equal to 0. So in place of S31 we can write 0. Next, S23, so in place of S32 we can write S23. S33 equal to 0 and S34, right? Next, S14, so S41 equal to S14, so in place of S41 we can write S14. Next, S42, S42 equal to S24, if S24 equal to 0 then S42 equal to 0. Next, S34 and S44 equal to 0. Okay, so 4 ports are perfectly matched to the junction, then we can write S44 also 0. So from the unity property, S into S complex conjugate equal to I, so 0 S12 0 S14, S12 0 S23 0, so 0 S23 0 S34, S14 0 S34 0, right? So from this we can write, so multiply R1 C1. If you multiply R1 C1, so S12 square plus S14 square equal to 1. Okay, multiply row 1 column 1. Then we get S12 square plus S14 square equal to 1. And multiply R2 C2. So from the matrix, multiply R2 C2, we get S12 square plus S23 square equal to 1. And multiply R3 C3. So it becomes S23 square plus S34 square equal to 1. So and multiply R4 C4. S14 square plus S34 square equal to 1. So here compare 3 and 4 equations and 5 and 6 equations. From 3 and 4, S14 equal to S23. Okay, so if compare these 3 and 4 equations, then we get S14 equal to S23. If you compare 5 and 6 equations, we get S23 equal to S14. So here compare 5 and 6 equations, we get S23 equal to S14. Okay, if you compare these two equations 3 and 4, here we get S14 equal to S23, and if you compare these 5 and 6 equations, we get S23 equal to S14. And multiply R4 C1. Multiply R4 C1. Then we get S14 S12 complex conjugate minus S14 complex conjugate S14 equal to 0, right? So from this, so it is S34, S12 equal to S34, S12 equal to S34, right? And multiplying R1 C3, so S12 S23 complex conjugate plus S14 S34 complex conjugate equal to 0. Okay, so first multiply R1 C1, R2 C2, R3 C3 and R4 C4. Then multiply R4 C1, R1 C3, okay. So here S14 equal to S23 and S12 equal to S34. So let us assume that S12 is real and positive. Then we can write S12 equal to P. Substitute S12 equal to P in equation 6. So equation 6 is S14 square plus S34 square equal to 1, right? So substitute S12 equal to P. So then we get P into S23 plus P into S14 equal to 0. So P into S14 plus S23 equal to 0. S23 plus complex conjugate S23 equal to 0. Right? Here P not equal to 0, so it is a positive value. So here S23 is imaginary. S23 is imaginary. So let us assume S23 equal to JQ. Let us assume S23 equal to JQ. Substitute all these values in equation 2. Substitute all these values in equation 2. We get S equal to, so 0 P 0 JQ, P 0 JQ 0, so 0 JQ 0 P JQ 0 P 0. So it is the S matrix for the directional coupler. It is the S matrix for the directional coupler. Okay. So once again we will see what is directional coupler. So directional coupler is a 4-port waveguide junction. So to measure incident power, reflected power and SWR values, we are using this directional coupler, right? So the power from port 1 is coupled to port 4, not to port 3. It has 2 main waveguides and 2 secondary waveguides. Okay. So it has 4 ports, so that's why the S matrix is a 4x4 matrix. So due to symmetry, we have S12 equal to S21, S31 equal to S13, S23 equal to S32 and so on. So here the 4 ports are perfectly matched to the junction. Then we can write S11, S22, S33, S44 equal to 0. Okay. So that is about directional coupler. So next we will see what is the Faraday rotation. What is the Faraday principle? What are the Ferrite components? So Faraday rotation in ferrites. Faraday rotation in ferrites. Now Gauri Priya. One second. Gauri Priya. Okay, I'm getting the disturbance. Okay. So Faraday principle states that if a circularly polarized wave is made to pass through a ferrite rod which has been influenced by the magnetic field, the axis of polarization gets tilted in clockwise direction. The amount of tilt depends on strength of magnetic field and shape and material of the ferrite rod. Okay, what is the Faraday's principle? Faraday's principle states that if a circularly polarized wave, see here, it is a circularly polarized wave. If a circularly polarized wave is made to pass through a ferrite rod, so it is a ferrite rod. This wave is passing through this ferrite rod. If a circularly polarized wave is passing through a ferrite rod which has been influenced by the magnetic field, here the axis of polarization gets tilted in the clockwise direction. So it is a tilted polarized wave, right? Here the axis of polarization gets tilted in clockwise direction. Okay. So if the circularly polarized wave is passing through the ferrite rod, so due to the influence of magnetic field, this wave is tilted. So the axis of polarization gets tilted in clockwise direction. So here the amount of tilt depends on strength of magnetic field. Here this amount of tilt depends on the strength of magnetic field and the shape of the ferrite rod and material of the ferrite rod. Okay. Here the amount of tilt depends on strength of magnetic field and material of the ferrite rod. The ferrite materials are oxide based components in the form of MnO and Fe2O3. So ferrite materials are oxide based components in the form of MnO and Fe2O3. The ferrite rods are obtained by firing powdered oxides of materials at 1100 degrees centigrade or more. The ferrite rods are obtained by firing powdered oxides of materials at 1100 degrees centigrade or more. So ferrites exhibits a strong magnetic property. Okay. So that is the Faraday's principle. The circularly polarized wave is passing through a ferrite rod. So due to strong magnetic field, it's tilted in the clockwise direction. So the axis of polarization gets tilted in the clockwise direction. The amount of tilt depends on the shape of the ferrite rod and material of the ferrite rod and strength of the magnetic field. So that is the principle of Faraday's rotation. Okay. So next we will see how the Faraday's principle is involved in this gyrator, isolator and circulator. So it is a gyrator. See this diagram? It is a gyrator. So gyrator is a two-port device. It has a relative phase difference of 180 degrees. Gyrator is a two-port device. It has a relative phase difference of 180 degrees. That is, the transmission from port 1 to port 2. See here, the transmission from port 1 to port 2, it has a phase shift of 180 degrees. And there is no phase shift for transmission from port 2 to port 1. Okay. So it is a two-port device. Gyrator is a two-port device. It has a phase difference of 180 degrees in the transmission from port 1 to port 2. And there is no phase difference and there is no phase shift for the transmission from port 2 to port 1, right? From port 1 to port 2 it has a phase shift of 180 degrees. From port 2 to port 1 there is no phase shift. Okay. See here, it consists of a piece of circular waveguide. So it is a circular waveguide. It consists of, the gyrator consists of a piece of circular waveguide with the transition to a standard rectangular waveguide at both the ends. Okay. So it is a rectangular waveguide. So gyrator consists of a piece of circular waveguide with the transition to a standard rectangular waveguide at both the ends, at the two ends. So next, a thin circular ferrite rod is located inside the circular waveguide. See here, it is a circular waveguide. At both the ends, we have rectangular waveguides. So inside the circular waveguide, we have a thin ferrite rod. A thin circular ferrite rod is located inside the circular waveguide, and the waveguide is surrounded by a permanent magnet. Which generates a DC magnetic field for proper operation of the ferrite. Right? So the gyrator consists of a circular waveguide. Inside the circular waveguide, it has ferrite rod. Right? Here the ferrite rod is tapped on both ends to reduce the attenuation. Here this ferrite rod is tapped on both ends. It is to reduce the attenuation. Here the ferrite rod is tapped at both ends to reduce the attenuation. Okay. So see the gyrator diagram. So here from port 1 to port 2 we have 180 degrees phase shift, and port 2 to port 1, so we don't have any phase shift, right? So it consists of circular waveguide and rectangular waveguide at the end, at the both ends of the circular waveguide. And inside the circular waveguide, the ferrite rod is placed inside the circular waveguide. Okay. If you see the working of this gyrator, when a wave enters at port 1, so it is a port 1. It is a port 1 and it is a port 2. When a wave enters at port 1, its plane of polarization rotates by 90 degrees because of the twist in the waveguide. And it again undergoes a Faraday rotational principle. So through 90 degrees because of ferrite rod, and the wave comes out of port 2 at a phase shift of 180 degrees. Okay. See here, when a wave enters at port 1, here the wave is entering at port 1. So it rotates by 90 degrees. See here, it rotates by 90 degrees because of the twist in the waveguide. So the wave entered at port 1 and it rotates by 90 degrees because of this twist in this waveguide, and this 90 degrees wave undergoes to Faraday rotational principle. So at port 2 we have the phase shift of 180 degrees. So 90 degrees and again 90 degrees. So 90 plus 90, 180 degrees, right? So here the phase shift from port 1 to port 2 is 180 degrees. Okay. So when the same wave enters at port 2, it undergoes a Faraday rotation through 90 degrees in the same direction, because the twist, this waveguide gets rotated by 90 degrees in anti-clockwise direction and comes out of port 1 with 0 degrees phase shift. Right? So this is about gyrator. So first, what is Faraday rotation principle? So when a circularly polarized wave is made to pass through a ferrite rod which has been influenced by the magnetic field, so the axis of polarization gets tilted in clockwise direction. So the amount of tilt depends on the strength of the magnetic field, shape of the ferrite rod, and material of the ferrite rod. Okay, here the ferrite materials are Fe2O3 and MnO. And if you see the gyrator, so it is a 2-port device. Gyrator is a 2-port device. It has a relative phase difference of 180 degrees. Transmission from port 1 to port 2 and no phase shift for transmission from port 2 to port 1. So it consists of a piece of circular waveguide with a transition to a standard rectangular waveguide at both the ends. And a thin circular ferrite rod is located inside the circular waveguide, and the waveguide is surrounded by a permanent magnet which generates a DC magnetic field for proper operation of the ferrite. And this ferrite rod is tapped at both ends to reduce the attenuation. Okay, so when a wave enters at port 1, so its plane of polarization rotates by 90 degrees, and it again undergoes Faraday rotation through 90 degrees because of ferrite rod, and the wave comes out of port 2 at a phase shift of 180 degrees. But when the same wave enters at port 2, it is coming to port 1 without any phase shift. Okay, so that is the Faraday rotation principle and the working of gyrator. In the next class, we will see about isolator. We will discuss about isolator and circulator. So with this, I am going to stop the presentation. If you have any doubts, you can ask me.